Thank you. So I'm Jory Denny, and this is a dynamic region bias rapidly exploring random trees. And it's going to be a combination of a new tool to be used by possibly many planners and also a RRT based around that tool. And this is joint work with Reed Sandstrom, Andrew Brager, and Nancy Amato. So we're going to look at the basic motion planning problem in this work. So we have a holonomic robot moving from a start to a goal, and we're trying to compute a path, which of course is a p-space hard in the general case because of narrow passage, other motion constraints. And in many problems, when we think about this, there's some relation to the 3D workspace for many types of problems. And so a question we can ask is, how can we exploit this relationship to improve the efficiency of sampling-based planners? And so something I'll put a plug for our last wafer paper. We looked at user-guided planning, and here's a video where a user can steer a region through a space, and the robot might be high-dimensional, but we can utilize this information to get a really effective planner. And there's other ways to do this. Maybe we have some complex heuristics, or maybe we have some topological analysis of the free workspace, and that's what we propose in this work. So what we're going to do is we're going to compute what we call an embedding graph, which is some representation of the free workspace. And in particular, we're going to use something from Morse theory called a Reeb graph. And to give kind of a simple example of a torus, it shows and basically encodes the critical points of the evolution of a function along a topological space. So for the torus, we can see the Reeb graph on the right. And what's really nice about this structure is it encodes that, hey, there's a left path and there's a right path. So can we exploit this in our planner to get some really nice benefits? And that's what we do in this work. And one of the benefits of this is it's a nice theoretical basis as a planning tool. And it has we introduce a temporal bias using this structure in our planner. And before we get to the details, I want to acknowledge that there are definitely some very important related work in using workspace information to bias a planner, and so I want to name two of them. So one is workspace importance sampling, and essentially what they do is they tetrahedralize the environment, and they use this tetrahedralization and a weighting over the tetrahedrons to bias PRM sampling. And it's very important work, very, very nice results to bias PRM planners. Another work is Cyclop, and this combines a discrete search over the workspace decomposition. Oh, just a second. It combines a discrete search over the workspace decomposition to bias an RRT planner. And kind of to differentiate between this is that we're having a smaller structure to represent our workspace than either of these works. So to go over our planner for this, is the first thing we do is we have a little pre-computation to compute our embedding graph, and we'll go over that in a second. And it might look something like the pink in this environment. And then what we're going to do is we're going to compute something that we call the flow graph. And the flow graph just says, well, which paths should we explore in our planner to bias our search? And if you notice from the start to the goal, some of those edges were pruned because they weren't really relevant to our search. And then we create some initial regions and use these regions to bias our RRT growth. Okay, and so we can see that when we're trying to explore both passages, both regions will bias the planning. So to look at how we compute the embedding graph, essentially what we do is we're going to start by computing a tetrahedralization of the environment. And then there's this nice work from the graphics community to construct a Reeb graph from the tetrahedralization. And the general idea of how it works is basically combines nearby tetrahedron that represent one part of the space. So it groups them together. So we get a nice representation. And then we're going to go back to the workspace to embed this Reeb graph. And so we have now a nice embedded spatial graph that we can use to bias planning. For the flow graph, essentially what we do is we just perform a breadth-first search from the start to the goal. That way we can find a directed version of the graph, and then we backtrack along the directed edges to figure out which edges we can prune. And then to bias our search, 4 general steps. Essentially what we do is we make a region-biased RRT extension, which simply randomly selects a region, and then from that region picks a workspace point to bias the C-space sample. And then we can advance the regions along the flow edges. So if the planner made sufficient progress, let's move the regions. And this introduces this temporal bias of our planner. And then we can delete useless regions, and how we define useless in this work is just maybe it failed too many times. So fails too many times, we can delete a region. And then also if we reach a new node of our flow graph, we would like to create new regions. And what's nice is that creating the regions, sampling from the regions, deleting useless regions is really not a lot of overhead over the standard RRT, and we bring in a whole lot of bias into the RRT, which is very nice. So to show a video of the whole planner, here's a complex 3D maze. What's shown in green is the flow graph. So you can notice right here, edges are pruned that are not really relevant to the graph search. And then I'm going to slow down the planner when we get there by 3 times, we'll say. And you can see even then how fast it explores. And so the region is shown as a sphere. So to look at this experimentally, first let's look at how we can use this in holonomic problems, and then we'll show a demonstration of it for a non-holonomic problem. But let's take these complex 3D environments, and some of them have multiple paths to the goal, some of them do not. And some of them actually have false passages. So in this maze tunnel in the first picture on the left, some of the passages can't actually be traversed by the robot. And our algorithm nicely handles that. So I'll break these results into a few different slides. So first, I want to look at some of the base environments where all of the planners can solve this, and we compare against RRT, dynamic domain RRT, Cyclop, and workspace information sampling, workspace importance sampling, sorry. And what's nice is in these problems, our method, which is shown in red, performs better. Okay, and so we have a lower time, it's significant, and that's very nice. And now when we look at the more complex environment, so our parking garage scenario, and this really complex 3D maze, again, we have benefit over the other workspace bias planners, and can even solve some problems that they cannot. Okay, so we really try to push the boundary of what can be solved in a very complex workspace. So additionally, we looked at a non-holonomic problem, just to show that yes, we can apply this to that kind of domain. And here we're showing our planner. Again, it's in red. The unfortunate part of the story is we're not quite able to overcome the performance of Cyclop in the non-holonomic problems. And looking at the technical details, what we believe, and we're looking into this right now, is that Cyclop also introduces not just the workspace bias, but also a way to bias the neighborhood finding strategy. And so I think we can leverage that in our algorithm as well to possibly overcome this difference. And so a little bit of dirty laundry before I finish up. So one thing in our embedding graph that would be something to try and look at is maybe trying to modify the embedding graph to improve the clearance of it. So right now what can happen is the embedding graph shown in pink can kind of get really close to those corners in an environment, but this can be very problematic to try to extend our RRT in that way. Okay, and so that's something we might look at, maybe modifying the embedding graph to overcome that. And this is kind of in relation to this, but more complex in a, like a 12-dimensional state space, is sometimes there's just a really bad extension where it always shows up when we look at our nearest neighbor. And so we try to repeatedly extend from that, and we fail a lot. And so there's something that we need to look at also in that domain for the kinematic version of this problem. And then, lastly, to overcome that difference to Cyclop is we'd like to also exploit this Reeb graph in our neighbor selection strategy to reduce the number of neighbors and hopefully speed up our neighborhood selection strategy. So with that, I will conclude, and if you have any questions, I'll be happy to take them. Thank you.
just before one short question. Did you try or could you say a few words about the applicability of the methods to articulated systems?
Say again?
What about the applicability of the technique to articulated robots?
Oh, to articulated robots, yes. So there isn't inherent limitation to using this REAP graph. What it really comes down to is we assume that there's a relationship between the C-space solution path and a path in workspace. So as long as that holds, you can use the same strategy for an articulated robot. And so we didn't do an experiment in this paper, but we have seen that in, I guess, the predecessor of this method that we used. Yeah.
Questions? Yes?
Thanks for your nice talk. I have a two-part question. The first has to do with, you mentioned deleting different regions when you have repetitive failures, and I believe in the paper you said it is tau, some type of threshold. How important, well, first off, how did you determine what that threshold was for the different examples you gave, and how much of an influence was it in the resulting runtimes? And as the second part, in your dirty laundry slide, you mentioned that sometimes the planner gets stuck and you have these high repetitive rates.
Mm-hmm.
When you delete these regions and you have these high repetitive failures, it seems like you could delete all the regions and then call into question the probabilistic completeness of the algorithm. So if you could mention that as well,
Yes.
that'd be great.
So I'll actually answer the second part of it first, which is in relation to the probabilistic completeness. So one thing we do consider is we consider the entire workspace as a region still. And so there's always a probability to select the original problem and not use our bias. So we are still probabilistically complete. So if you delete all the regions, it just reduces to a standard RRT. And what's even nice about it is once the RRT reaches the next REAP node, we go back to using that bias again. So we can handle that case. And you are right, and it should have been on the dirty laundry slide, that this tau to how we select when we delete is a problem. And we basically selected just a nice value for our experiments, but it's something to look into at what maybe it should be, and maybe it's something that adapts over time. And so maybe we adjust our probability to sample from it instead of just deleting the region. And so I think that's an important area that we should look into in the future.
Joshua? Yes?
Have you extend the algorithm to take into account path quality?
I definitely think so. And I think when we do this, it will be very important not to just do it heuristically, but to show that it provably can be the same. So considering like asymptotic optimality, I definitely think that's an important extension that we can do.
Okay. So let's thank again the speaker and move to the.